Ever get that feeling like, your brain is like this crazy powerful computer
Mm.
and you're just starting to figure out how to turn it on?
Mm.
Today we're going deep on one of its most, I think, underappreciated parts.
Okay.
Dendrites.
Yeah.
They're not just like wires, they're like, the brain's processing powerhouses.
Yeah, see, for the longest time, I think a lot of people, scientists included, thought dendrites were just these passive cables in the brain. They just shuttled the messages along,
Right.
didn't have much say in the matter,
Right.
just kind of like a highway system.
Not exactly the stars of the show.
No, not at all, not at all. But Wilfred Rall, a neuroscientist who had a real knack for math, decided to challenge that assumption.
Okay.
His 1962 paper, Theory of Physiological Properties of Dendrites. It completely changed the game.
Okay, now this is where, in my mind, I always imagine those old, black and white photos of scientists with like the crazy hair hunched over these like, pages and pages of equations.
Right.
So what did he find? What did Rall uncover that was so groundbreaking about dendrites?
Well, he dove deep into, that really intricate world of dendrites. And he used math to really model their complex shapes and their electrical properties. And what he discovered was that dendrites aren't just passing information along. They're actively processing it.
Hold on. I need a little bit of a refresher here. We're talking about those tree-like branches of neurons, right?
Yes.
What does it even mean for them to be processing anything?
So it's more than just, relaying the signal from point A to point B. It's about, imagine like a busy intersection with traffic flowing in from all directions.
Okay.
The dendrites act like the traffic lights at that intersection.
Okay.
They're directing and managing the flow of information based on where those signals are landing and how strong they are. So they determine which signals get amplified, which ones get toned down, and how all of that information gets integrated before it's passed on to other neurons.
Okay, so that's like a much more like active and dynamic picture than just like some passive wiring.
Absolutely.
But dendrites, they're incredibly complex, these branching structures. How do you even begin to study something that's so intricate?
Well, that was the challenge that Rall was really, determined to tackle head on. He used his mathematical skills to kind of simplify those complex shapes. And he represented them as cylinders without losing the essence of their electrical properties. Imagine taking a big, sprawling oak tree and, representing its branches as this series of interconnected cylinders.
So it's like creating a simplified model, but it still captures those like key features, right?
I see, exactly.
Kind of like those subway maps.
Exactly. Right.
That use just like lines and dots to represent what's actually this incredibly complex system.
Yeah, you got it. It's about making that complexity manageable so you can actually study it, how those signals flow through those branches.
That's a pretty ingenious approach. Using math to create like a user-friendly version of like the dendritic world.
Yeah.
But what did that actually reveal? Like what came out of this simplification? So Rall, he gives us like the tools, right, to understand these really intricate dendrites.
Yeah.
But how do they actually put all that branching complexity to work? Like what's happening at the level of, individual signals?
Yeah, that's where we get into this fascinating world of synaptic activity.
Yeah.
It's like, the language of neurons.
Right, the sparks flying between brain cells.
Exactly.
How do dendrites fit into that whole conversation?
So think of it this way. Neurons talk to each other using these like brief electrical impulses, little bursts of energy.
Okay.
And these signals are transmitted at these specialized junctions called synapses.
Okay, so synapses are like the meeting points where the neurons are like shaking hands and, swapping information.
Exactly. Now, what Rall's work showed us is that it's not just about the strength of that handshake, but also its location on the dendrite.
Wait, so where a signal lands on a dendrite actually matters?
It's all about location.
Really?
Yeah, he found that signals landing closer to the soma, that's the neuron's main body, they have a much faster and stronger effect than those that are, further out on the dendritic branches.
So it's kind of like if you're closer to the source of a sound, it's going to be louder and clearer.
Exactly.
Than if it's coming from, further away.
Precisely. Imagine someone whispering a secret, right in your ear, versus shouting that same secret from across a crowded room.
Right.
That whisper, even though it's quieter, it's going to have a much more immediate and direct impact.
Right, because of where you're hearing it, not necessarily how loud it is.
Exactly.
Okay, that makes sense. So it's not just about the signal itself, it's about how and where it's received. So dendrites aren't just like relay stations, they're more like, I don't know, nightclub bouncers or something.
Yeah.
They decide which signals get the VIP treatment and which ones are stuck, waiting in line outside.
I love that analogy.
Yeah.
And it really gets to this point that dendrites are filtering and prioritizing
Okay.
all the time.
Yeah.
All this information they're receiving, they're making these decisions about which signals are important enough to get amplified and passed on to the soma.
So they're like these tiny little computational units
Yes.
weighing the evidence, making these judgment calls on the fly.
Exactly. They're constantly integrating all those incoming signals,
Mhm.
some of which might be excitatory, kind of pushing the neuron toward action,
Mhm.
and others inhibitory, which dampen the activity.
Yeah.
So it's like this constant dance between these go and stop signals.
Okay, let's break that down a little bit more.
Yeah.
Because, excitation versus inhibition, that sounds a lot like my brain trying to decide whether or not to hit the snooze button in the morning.
It's a struggle.
Yeah.
Many of us know well.
Yeah.
But on a neuronal level, it's this interplay, this push and pull between excitation and inhibition that allows our brains to function with this, remarkable precision and avoid just getting completely overloaded.
So how do dendrites manage that balancing act? What's their secret? So they're like these master conductors, these incredible integrators of information. But how do they actually do that? What's like their secret sauce?
It comes down to flexibility.
Okay.
Dendrites can actually adjust their electrical properties. So they're fine-tuning their response to all those incoming signals. They're not static, they're dynamic.
Okay.
They're constantly adapting.
So it's like they have their own little like internal volume knobs.
Yeah.
Turning some signals up, some signals down, depending on, what the situation calls for.
Yeah, and they can even adjust, like the wiring itself,
Oh, wow.
strengthening or weakening those connections between synapses, depending on how often they're used.
So it's like, this is how we learn.
This is how we learn. It's this incredible plasticity
Yeah.
that allows our brains to learn and adapt.
Throughout our entire lives.
Exactly, yeah.
Wow. Okay, so this is where we get to the really big picture.
Yes.
Because if these tiny little branches are doing all this complex processing, that has to have huge implications for like how our brains function overall, right?
Absolutely. Rawls' work, it was a paradigm shift.
Okay.
He showed us that intelligence isn't just about, how many brain cells you have.
Right.
It's about these intricate computations happening within each one, thanks to dendrites.
And this new perspective, it kind of opens up this whole new way of thinking about brain disorders, too.
Absolutely.
Right.
Yeah, think about something like epilepsy.
Okay.
We know now that disruptions in how dendrites function, especially that balance of excitation and inhibition,
Right.
that can contribute to seizures.
Wow.
And with Alzheimer's disease, one of the early signs is actually damage to dendrites,
Huh?
which impairs memory and cognitive function.
It's amazing how something so small
I know.
can have such a huge impact on, like, our health and who we are.
It really is incredible.
It makes you really appreciate the complexity of, what's happening inside our own heads.
It does. And, we're still uncovering the mysteries of these structures.
Right.
Rawls' work was groundbreaking, but there's still so much more to learn.
That's the beauty of science, right?
Yeah.
Every answer leads to more questions.
Absolutely.
So I guess next time you're, like, wrestling with a tough problem, just remember
Yeah.
those intricate dendritic trees in your brain are hard at work, integrating information, making connections,
Yeah.
constantly adapting to the world.
It's pretty amazing.
Who knows what other secrets those tiny branches hold?